In this section, we're going to be going over indeterminate forms and L'Hopital's rule. So let's do these first examples. Let's say we try to evaluate these following limits using direct substitution. So the first one, we have the limit of ln of x over x minus 1 as x approaches 1. Let's say that we try to do direct substitution. That would be the ln of 1 over 1 minus 1. The ln of 1 is 0 over 1 minus 1 is 0. So we actually get 0 over 0. So 0 over 0 actually does not tell us anything. This is an example of indeterminate form. Let's go to the next one. The limit of e to the x over x squared as x goes to infinity. So let's pretend like we were plugging in infinity, even though we wouldn't actually be plugging in infinity because it's not a number. That'd be e to the infinity over infinity squared. E to the infinity is just infinity. Infinity squared is infinity. So infinity over infinity, this actually doesn't tell us anything again. This is another version of indeterminate form. And for this last one here, we have the limit of x times e to the x as x approaches negative infinity. So let's pretend like we would plug in negative infinity. That would be negative infinity times e to the negative infinity. And we could rewrite that as negative infinity divided by e to the positive infinity, make the exponent positive by putting it in the denominator. So this would end up being negative infinity over infinity. So once again, another version of indeterminate form. And just like I mentioned here, don't actually plug in negative infinity. That is not correct. So all of these are examples of indeterminate form, 0 over 0 and plus or minus infinity over infinity. And this tells us nothing about the actual limit. This is not the answer to the limit. And it does not mean that the limit does not exist. It means that we're going to have to do something else to actually figure out what this limit is. So that brings us to L'Hopital's rule. So L'Hopital's rule is essentially going to be our way around evaluating these types of limits. So let's say that we have functions f and g and they're both differentiable. And suppose that the limit of f of x as x approaches a and the limit of g of x as x approaches a both equal 0, or they both equal plus or minus infinity. Then we have this L'Hopital's rule right here. The original limit as x approaches a of f over g is going to equal the limit of the derivative of f divided by the derivative of g as x approaches a. So what we can do is if we have one of these limits, we do direct substitution, we get indeterminate form. We apply L'Hopital's rule, which is taking the derivative of the numerator, taking the derivative of the denominator separately, and then redoing the limit. And make a little note, this is not the quotient rule. I know it's two things being divided. You're doing the derivative of the numerator and denominator separately. And let's say that you did this method, you did L'Hopital's rule, and then you redid the limit. If you got indeterminate form again, you can actually continue to do this method until you get an answer. So let's do that the first example, I believe it was. Find the following limit. We have the limit of ln of x over x minus 1 as x approaches 1. Always try to do direct substitution. We would get ln of 1 over 1 minus 1, which is 0 over 0. And we know this is indeterminate form, so we apply L'Hopital's rule. So L'Hopital's rule says if we are evaluating this limit, I'm just going to rewrite it. If we're evaluating this limit, what we can do is we can say that this equals the limit as x approaches 1 of the derivative of the ln of x divided by the derivative of x minus 1. So we're going to do the derivative of the numerator and denominator separately, and then redo the limit. So the limit as x approaches 1, the derivative of ln of x is 1 over x. The derivative of x minus 1 is 1 minus 0, so just 1. So now we have the limit as x approaches 1 of 1 over x, and now we can perform direct substitution. Plug it in, 1 over 1, we get an answer of 1. So this whole limit of the ln of x over x minus 1 as x approaches 1 equals 1 using L'Hospital's rule. So a couple more examples, we're basically doing the first two examples that were on the first page. Limit of e to the x over x squared as x approaches infinity. We attempt direct substitution. And if we do that, we would end up getting e to the infinity, which is infinity, over infinity squared, which is infinity. So indeterminate form, apply L'Hospital's rule. So we go ahead and we say the limit as x approaches infinity of e to the x over x squared is going to equal the limit as x goes to infinity of the derivative of the numerator divided by the derivative of the denominator. So we go ahead and we take the derivative of the numerator. The derivative of e to the x is e to the x. The derivative of x squared is 2x. And the issue for this is that if we try to do direct substitution, we get infinity over infinity again. So we need to apply L'Hospital's rule again, and we do the derivative of e to the x. So d dx of e to the x divided by d dx of 2x, and we get the limit as x goes to infinity. The derivative of e to the x is e to the x. The derivative of 2x is 2. So now we can actually apply direct substitution. This would be, I'm not going to actually plug in infinity. E to the infinity is obviously infinity. Infinity divided by 2 is infinity. So we get an answer of infinity. Or if you want to think of it as like this, where you bring out the 1/2 out front and do 1/2 times the limit as x goes to infinity of e to the x. Maybe that's a better visual for you. Limit as x goes to infinity of e to the x is obviously infinity. E to the infinity is infinity. Infinity divided by 2 is still infinity. Either way is fine. So this limit ends up being infinity. Which this is one where maybe you could have thought of just by looking at it. E to the x is an exponential. X squared is just a quadratic. The exponential is going to blow up a lot faster than the quadratic. So as x goes to infinity, that fraction would go to infinity as well, because the numerator increases faster than the denominator. Okay, next one. Limit as x goes to infinity of ln of x over the cube root of x. So we try to plug in infinity. The ln of infinity is infinity. The cube root of infinity is also infinity. So indeterminate form. And we apply L'Hospital's rule. So we have our original limit, and it's going to equal the limit if we take the derivative of the numerator and denominator separately. So derivative of ln of x, and for the denominator, the cube root we should know is x to the 1/3. So a cube root is an exponent of 1 over 3. And now we have the limit, derivative of ln of x is 1 over x. And the derivative of x to the 1/3 is power rule, 1/3 x to the negative 2/3. And now before we do anything, we should rewrite this. Limit as x goes to infinity. And this would be 1 over 3 x times x. Or actually, the 3 would be in the numerator. So if we thought of this as keep, change, flip, just so we don't mess that up, We keep and then change this one to multiplication, and then we flip the second one, and then we multiply straight across. So it would be 3 over x times x to the negative 2/3. We would add the exponent. So 1 plus negative 2/3 would be x to the 1/3, or the cube root of x. Okay, so that's from adding these exponents together to create one base for them. And now we can go ahead and plug in infinity. So once again, don't actually plug in infinity. If we have 3, if you want to bring the 3 out front also, you can 100% do that. This though, right here, the cube root of x as x goes to infinity is going to approach infinity. It might not do it super quickly as other functions might, but it's still going to end up going to infinity. So we have 3, I'll bring out the 3 just so we can remember that we can do that for a better visual. 1 over the cube root of x. And now we get 3 times, if you have 1 over infinity, 1 over infinity is going to be 0. Right? So if we had this function, 1 over the cube root of x, as x gets larger and larger and larger, that fraction is going to get smaller and smaller and smaller. It's going to approach 0. So this limit actually equals 0. Okay, so a few more examples here. We have the limit as x goes to 0 of tangent x minus x all over x cubed. And if we try to plug in 0, tangent of 0 is 0. So we'd get 0 minus 0 all over 0 cubed, which is obviously 0 over 0. So we get indeterminate form, apply LHospitals rule. So we have our original question is going to equal the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. So the derivative of tangent is secant squared. So that's going to be secant squared of x minus the derivative of x is 1. The derivative of 3x, or the derivative of x cubed, is 3x squared. Okay, I'm just going to move this over a little bit. So if we tried to plug in 0 right now, we would actually end up getting 0 over 0 again. We'd get indeterminate form. Secant of 0 equals 1, so 1 squared is 1. 1 minus 1 for the numerator is 0, and 3x squared would obviously be 0 as well. So we get indeterminate form, apply LHospitals rule again. So we're going to do that again. Limit as x goes to 0, derivative of the numerator divided by derivative of the denominator. So for the derivative of secant squared, that's going to be chain rule. We bring the 2 out front, leave the inside alone, subtract 2 from the numerator, times the derivative of the inside. The derivative of the inside is the derivative of secant, which is secant x times tangent x. Derivative of the denominator is 6x. And I'm going to pull a little bit of a trick here. First, I'm going to write 1/3 out front from the 2 divided by 6 is 1 over 3, just a constant. I'm going to split this up. I'm going to do the limit as x goes to 0. Secant times secant is secant squared. And then I'm going to do times the limit as x approaches 0 of whatever was left over, which was tangent of x over x. So this is just rewriting it using limit properties. And the reason why this is nice is because this limit, the limit of secant squared as x approaches 0, that's direct substitution. Secant of 0 is 1, so 1 squared is 1. So that limit's just 1. So we end up getting 1/3 times 1 times the limit as x approaches 0 of tangent x over x. I didn't really touch that one yet, so I'm just going to bring it down. We took care of one of kind of the chunks. Let's take care of the next chunk now. So now if we went ahead and we plugged in, if we did direct substitution, do that on the side. If we tried to plug in tangent of 0 over 0, we would get 0 over 0. So let's apply L'Hopital's rule one more time. So we end up getting 1/3 times the limit as x goes to 0. So derivative of numerator and denominator, which gives us 1/3 times limit as x approaches 0. The derivative of tangent, secant squared. Derivative of x is 1. Now we can do direct substitution because the limit as x approaches 0 for secant squared is just 1. So the final answer is 1/3 times 1, which gives us a nice 1/3. Okay, so that one a little tricky because we had to do L'Hopital's rule a couple times, and then we were able to rewrite it using limit properties. Okay, 2 more examples. We have the limit of x times e to the x as x approaches negative infinity. We attempt to do direct substitution. Negative infinity times e to the negative infinity. We did this one, I believe also, which is negative infinity over e to the positive infinity, which is negative infinity over infinity. So we go ahead and apply L'Hopital's rule to this original limit. And the issue here is that this is not a quotient, right? It's not a fraction. We have to rewrite this as a fraction to use L'Hopital's rule. So what we can actually do is we can rewrite this as the limit as x goes to negative infinity of x over e to the negative x. So all I did was rewrite e to the x as 1 over e to the negative x, just switching the exponent from positive to negative and putting it in the denominator. But now it's a fraction, now it's a quotient, so we can apply L'Hopital's rule. So derivative of the numerator, derivative of the denominator, and the derivative of the numerator is the derivative of x, which is 1. Derivative of e to the negative x is chain rule. We get negative e to the negative x. And before we do anything here, let's rewrite this. I'm going to bring the negative out front. Negative limit as x goes to negative infinity of e to the negative, or e to the positive x, because we're changing it from denominator to numerator, so the exponent changes, positive or negative to positive. And now we can plug in, imagine plugging in negative infinity. E to the negative infinity is 1 over e to the infinity, which is 1 over infinity, which would be 0. So this answer would be negative 0, which is just 0. Okay, so we really don't want to write the portion that I just wrote. If you do want to write it out, because it is a nice visual of what's happening, that's fine. But technically you should not have that as part of your work. Okay, so one more example here. We have the limit as x approaches negative 2 of x squared minus 4 over x plus 2. So before we do anything, notice that we could do this limit by factoring the numerator and canceling common factors, and then doing direct substitution. So maybe check that with your answer. But let's do this using L'Hopital's rule. So we try to plug in negative 2 right away using direct substitution. And you can see that this gives us 0 over 0. So we go ahead and apply L'Hopital's rule. Limit as x approaches negative 2 of x squared minus 4. We're going to now take the derivative numerator and denominator separately. And the derivative of the numerator, the derivative of x squared minus 4, is 2x. The derivative of x plus 2 is 1. So all this is the limit as x approaches negative 2 of 2x. And now obviously we can do direct substitution. We plug in negative 2. 2 times negative 2 gives us an answer of 4. Okay, so like we said, this isn't technically one where we needed to use LHospitals Rule. We could have done it another way. But as soon as you get indeterminate form by plugging directly in, then we could always do LHospitals Rule. Okay, so that is it for this chapter.